Hi students, welcome back. Today we will be studying about simple DC motor. What is a motor? A motor is a device which converts electrical energy into mechanical energy. So what is a electrical motor? Is a device which converts electrical energy into mechanical energy. Here in this picture, as we can see, here is a fan. And what happens when we switch on the fan? The wings or the parts starts rotating. This shows that whenever there is an electrical connection or electrical energy given, then what happens? The fan starts rotating. So electrical energy is being converted to mechanical energy. Here, as soon as the fan starts rotating, it converts into mechanical energy, and this happens due to that motor which is present on the back side of the fan. See, here it is showing us electrical energy is being converted to mechanical energy, and that is due to this motor which is present at this back side. This is the electrical motor. We will be studying about the simplified electrical motor. This is the simplest version of electrical motor, and it works on a principle which I will state in this diagram. It says that whenever a current carrying conductor is placed in an electric field, it experiences a mechanical force. Let's see that diagram once more. See here, as you can see here, there is a current carrying conductor placed in a magnetic field. That is, the horseshoe shaped magnet is placed, and the current carrying conductor, because this conductor is placed is connected to a battery, and as soon as the electrical current flows through it, and this conductor is placed in a magnetic field. So whenever current flows through it, this conductor experiences a force or moves somewhere. So what are the parts used in a simple DC motor? It consists of a horseshoe shaped magnet. Here is an armature coil A, B, C, D. We can name as A, this corner as A, this one is B, this one is C and D. This is an armature coil A, B, C, D. Then a split rings. Here we can see a half ring, and that is known as split rings or commutator. This commutator is made of copper. Then there is a small black part here as shown in the figure. That one is known as a pair of carbon brushes, B1 and B2. These black part is known as carbon brushes. Then what we have? An electromagnet, horseshoe shaped electromagnet. Then a DC power source. This battery is a DC power source. So it is showing here as U-shaped magnet, armature coil, then split rings, then carbon brushes. This is a key, and this is the DC voltage supply. This is the armature coil. In reality, the armature coil is not a single turn. As we have seen in the figure, there is only a single turn which has been shown. But here, the armature consists of many turns. As you can see, there are various armature coils together. They are laminated together or placed together. But for simplification, I have been showing that figure for a single turn armature coil. This is the part which I will be dealing. Only a loop of a wire is shown for simplicity, as I have told you earlier. So one more thing, students, see, this diagram shows that the split rings and these are the carbon brushes, but the carbon brushes are not fixed to the slip ring, whereas this armature coil is fixed to the slip ring. Remember this carbon brushes is not fixed totally, it just gently presses the slip ring, whereas this armature turn coil is directly fixed with the slip ring. So now, how does this work? This works on a principle that whenever electric current is passed through a conductor placed normally in a magnetic field, a force acts on the conductor, as a result of which conductor begins to move and thus mechanical energy is obtained. The direction of this, whenever the key is open, no electricity flows and therefore no rotation and therefore no force and no rotation. So the direction of the force is determined by Fleming's left hand rule. Let's see what does this Fleming left hand rule states. If you put out your left hand in this form, that the thumb, the forefinger and the middle finger are perpendicular to each other, then what? If the forefinger points to the direction of magnetic field and the middle finger points to the direction of current, then the thumb shows the direction of force exerted. Now let's see how does a simple DC motor works. DC motor works on a very simple principle. We know that whenever a current carrying conductor is placed in a magnetic field or between two poles of a magnet, then it experiences a force in a particular direction, and the direction of the force can be determined by Fleming's left hand rule. Now this is a elementary arrangement of a single turn armature coil, as we have already studied that simple DC motor consists of an armature coil. This yellow part is the armature coil, and these two circular half ring, they are known as the slip rings of the commutator. This one is S1 and this is S2. Let's name it as S1 and this one is S2. Name this side A, B, C, D. This brush as B1 this side, and this side brush as B2, and this is the battery source. Now let's see one more thing, that the commutator, the DC current flows through the commutator to the armature coil. One more thing, the south pole is on the left hand side and the north pole is on the right hand side. So this AB side of the conductor or the armature coil is placed at the left hand side and the CD side is placed at the right side or near the north pole as of now. Let's see how does it work. Whenever the key is closed, the DC current flows through the armature coil. So whenever the key is closed, how does the current flows? It flows, the current always flows from the positive terminal to the negative terminal. So how it flows from the positive terminal? It gets to the brush B1, then the slip disc S1, then A, B, C, D, again back to S2, then B2 and then back to negative terminal. This is how the current flows. Now let's see. And this total slip disc part is known as commutator system. Whenever we allow the current to flow, current starts from the positive terminal and it flows through this one and it goes here and comes back like this to the negative terminal, as I have already said to you. Now let's see. The south pole is at the left side, the north pole is at the right side. Keep in mind of this one. Now what we will see, the current, let's see how does the current flows from here. The current goes from AB and again back to CD and it comes back like this. So now this whole total armature setup is in a magnetic field. The magnetic field is highlighted in this area. So and one more thing children, this magnetic field this armature is not attached to the north pole or to the south pole. It is it it can be, it can move freely. Let's see, it can move freely. And one more thing, now we have to determine, when we know that whenever current carrying conductor is placed in a magnetic field, it experiences a force which can be determined by Fleming's left hand rule. Let's see what does Fleming's left hand rule states. Fleming's left hand rule states that if current is in direction of the if current and magnetic field are both perpendicular to each other, then the thumb indicates the direction of force. Now let's put this Fleming's left hand rule here. Now let's apply Fleming's left hand rule for this side of the conductor, or AB of the conductor. What will happen if we put Fleming's left hand rule for AB side of the conductor? Let's see. Open your left hand in that manner so that the thumb and forefinger and middle finger are perpendicular to each other, as shown in the previous diagram. Then what, apply Fleming's rule. The magnetic field is always in the direction from north pole to south pole, so the middle finger points to the magnetic field. Then the forefinger is in direction of AB. The current direction here is shown in red color arrow marks. So the forefinger indicates the direction of current. So what will be the force direction? It is upward. It's clearly upward, right? So here what happens, the conductor AB moves upward. The direction of thumb indicates force and it is upward. Similarly, when we apply Fleming's left hand rule for this CD side, the current direction is opposite. Now if we apply Fleming's left hand rule to that one, then what happens, the direction of magnetic field is always here, north to south pole. Then you can see the thumb points downwards, so the force acts downwards. Now we can see here one more thing. See, the AB conductor, the AB side moves upward, and here what's happened, the CD sides goes downward. So originally it was in horizontal position. Now when force acts on it, what happens, it moves upward and this side moves downward. So this upward movement and downward movement produces a torque, and it moves to a vertical position, or it moves 90 degree. As you can see, there is a torque or a force. See, why we are saying it as torque or force? Because there is this side, there is one side we can see, as you can see the figure here, there is a equal force applied upward, and here a equal force is applied downward. So there is a torque produced, and it moves, the armature coil rotates 90 degrees. See, in the blue color diagram, it is shown that it has moved 90 degree. And now at this position, what happens? Let's see. Now at this position, the armature coil cannot stay for a longer time due to inertia of torque. What happens, inertia of motion, the armature coil will tend to stabilize or come back to its original position, that is horizontal position. So it won't stay here for a longer time, but due to inertia it rotates a little more and comes to horizontal again. Okay, now what happens, it will come back to its original horizontal position. But before that, when it remains at this stage, what happens? Let's see again. How does the current flows? From the positive terminal to the negative terminal, and there should be the closed circuit. The key is closed here, so it should flow. But what happens, the current flows through this one. This one is brush B1, and but here the slip rings are already rotated half, so there is no connection between the brush and the slip rings. There is an open connection, so current cannot flow through this. And when the current cannot flow, so there is no current flowing in the conductor arms of the armature coil. So what happens now? What is our first case? The If a current carrying conductor is placed in a magnetic field, right, then it experiences a force. So now what happens? Is this a current carrying conductor right now? No, as the though battery is closed, still there is no connection between the slip rings. So no current flows through the conductor or the armature coil right now. So what happens? There is no current flowing through this as the position of the slip ring is changed. But what happens due to inertia of motion? Suppose if you throw a stone to up, what it will it remain in up forever? No, it comes back down. Similarly, for due to inertia, so here also it can't stay in this position for a longer time. It momentarily comes back to its horizontal position. So now what happened? This AB side has turned here and the CD has come here. Now when it comes to an horizontal position, what happens? The AB side will come here and the CD will come here, right? Let's see the diagram. So it has moved. The arrow, red arrow shows that it has moved. What happened now? The AB side has come this side and the CD side has come this side. Now will the current flow? Yes, the current will flow because in this position it can flow. But whenever it is in vertical position, it doesn't allow the current to flow. So again, when the switch is closed means there is current flowing through this armature coil. Now again in CD, what happens? Current is flowing and it is under the influence of a magnetic field. So it will experience a force. Now again applying Fleming's left hand rule to this side and this side. What we can see, how does it move? Let's apply the Fleming's left hand rule to the both side. The CD has come this side, remember, and the AB is this side. So applying Fleming's left hand rule. Again stretch your fingers of your left hand in a perpendicular to each other as shown in this figure. Now we will apply this again to the conductor or armature coil. Again applying here, we will see that the force is upward. The direction of magnetic field is always in this direction. This blue color always indicates the direction of magnetic field. So here again the force, the thumb indicates the direction of force and it is upward. Similarly applying to this side, what happens to this side of conductor or AB? What happens? Again you can see that the direction of force is downward. The thumb indicates downward, so the direction of force indicate is downward. So what happens again? What does this side moves up and this side moves down? Again what happens? You can see that there is a 90-degree turn, but it won't stay in that vertical position for a longer time, and again it will rotate to a horizontal position. So what happens? We can see that due to this, the current keeps on, as long as the current flows through this circuit, it keeps on moving and keeps on moving in a clockwise rotation. Here we can see that the direction of thumb is downward, so it moves like this. As you can see in this figure, the armature coil is moving in this manner or in this fashion. So this is how it works. But in a practical DC motor, what we can see that here for simple DC motor, I have shown a single armature coil model. This model is for a single armature coil. But in a practical DC motor, in a practical fan, the fan you use at home, the table fan you use at home, or the mixer or grinder you use at home, that doesn't contain a single armature coil. It contains multiple armature coil. So what we will do now is that what are the ways of increasing the rotation of coil? The coil here is the armature coil. So what we can do to increase the speed of rotation? You must have got a fan which can move in one speed and a fan which can move in high speed, right? So what we can do to move it in higher speed? What we can do? First of all, we can increase the current in the coil. Secondly, increase the number of turns in the coil. There is a single turn armature coil that I have shown in the figure or in the video. But here what we can do for increasing the speed of rotation, we can use number of turns, more number of turns. Then what we can do, we can increase the area of the coil. Then fourthly, we can increase the strength of the magnetic field. To increase the strength of magnetic field, what we can do, we have to place a soft iron core inside the armature coil. The armature coil was like this, right? Rectangular. And inside it, if we place a soft iron core, that can increase the magnetic field. What is the function of commutator? Commutator was the slip rings S1, S2, that half circle slip rings. What does it do? It allows the current to flow in one direction. In the last part we saw that it is moving in a particular clockwise direction. It wasn't moving like this half here. No, it was moving in a particular direction, and that is possible due to this commutator. Hope you have understood this topic. Thank you for watching.